Try this instead. Don't imagine the night sky as empty. Imagine it as paused. The difference sounds small, but it changes everything. When something is empty, nothing is there. When something is paused, everything is still there, just waiting. I want you to hold that distinction in your mind, because the entire mystery begins to look different once you stop thinking about absence and start thinking about patience. For most of human history, we looked up and assumed the universe was silent because it was lifeless. And that assumption felt natural, almost comforting, because emptiness is simple. It asks nothing of you. But the numbers refuse to cooperate with that comfort. Our galaxy alone contains hundreds of billions of stars, and the observable universe contains trillions of galaxies, which means the stage is not just large, it is absurdly large. The kind of scale where even rare things should happen over and over again. Life appeared on Earth relatively quickly, once conditions allowed it. Intelligence followed after a few billion years, and nothing in the chemistry involved seems unique to this planet. Carbon behaves the same everywhere. Water forms under common conditions. Organic molecules appear in interstellar clouds, which means the universe looks less like a miracle that happened once and more like a process that should repeat. And yet, when we listen, we hear nothing. That silence has a name, the Fermi paradox, and it is deceptively simple. If intelligent life should be common, where is everybody? The longer you sit with that question, the more uncomfortable it becomes, because the usual answers all require something dramatic. Civilizations destroy themselves. Intelligence is impossibly rare. Interstellar travel is unattainable. Everyone is hiding. Each of these explanations removes voices from the universe, turning the silence into absence. But there is another possibility that does not remove anyone at all. It only changes what intelligence chooses to do. Suppose a civilization grows old enough to realize something we rarely think about, that thinking itself is a physical process, and like any physical process, it costs energy. Every computation produces heat. Every bit erased leaves a thermodynamic footprint. And that cost depends on temperature. In a colder environment, the same amount of energy can perform more computation, not slightly more, but dramatically more, because physics itself becomes more forgiving. Now look at the universe. It has been cooling since the Big Bang and will continue cooling for trillions of years. The background temperature slowly drifting toward absolute zero, which means the future is not just darker. It is computationally cheaper. The same energy spent far in the future could produce vastly more thought than if spent now. If you take that idea seriously, the rational strategy changes. Instead of expanding loudly, broadcasting signals, and burning energy in the warm, early universe, an advanced civilization might decide to wait, to store its resources, slow its activity, and enter a long dormancy while the universe cools from the outside. Such a civilization would look exactly like nothing. No signals, no waste heat, no obvious engineering. Just quiet. Not because it failed, not because it died, but because patience became the most intelligent choice available. Once you see that possibility, the silence above us stops feeling empty and starts feeling deliberate, as if the universe were holding its breath, not abandoned, not lifeless, but paused at a moment before something enormous resumes. There is a question that sounds almost childish the first time you hear it, and yet it leads straight into one of the deepest connections between physics and intelligence. Does thinking cost energy? Not metaphorically, not in the sense that your brain needs food, but in the strict physical sense. The same sense in which lifting a weight costs energy or lighting a bulb consumes power. For a long time, this question sat in the background because computation looked abstract, something mathematical rather than physical. But eventually, physicists realized that information is not separate from reality. It is embedded in it. And once you accept that, every computation becomes a thermodynamic event. Imagine a computer erasing a bit of memory. You had either a 0 or a 1. And after the operation, you reset it to 0. The information about what was there before is gone. And that irreversibility is the key. When information disappears, entropy increases, and when entropy increases, heat must be released into the environment. This is not an engineering limitation that clever hardware can avoid. It is a statement about the structure of physical law. The minimum energy required to erase a bit is proportional to temperature, which means the hotter the environment, the more expensive every computational step becomes. Once you see that, thinking stops being an abstract act and starts looking like a machine running inside a thermal bath, paying a small but unavoidable price every time it updates its state. Now place that idea inside the universe as a whole. Even empty space is not truly cold, because it is filled with the faint glow left over from the Big Bang, the cosmic microwave background, a uniform bath of radiation sitting at about 7 Kelvin, that is incredibly cold by everyday standards, colder than any natural environment on Earth, but it is not zero. And because it is not zero, it still imposes a cost on computation. Every calculation performed anywhere in the universe today is happening inside that thermal background, which means every civilization, every computer, every thinking system is paying the same fundamental tax. But the universe is expanding, and as it expands, that background radiation stretches and cools. Billions of years from now, it will be lower. Trillions of years from now, lower still, drifting toward absolute zero without ever quite reaching it. Here is where the logic becomes uncomfortable, because it introduces a simple comparison. Suppose you have a fixed amount of energy, some stored resource you could spend on computation. If you use it now, in the relatively warm universe we inhabit, you obtain a certain number of operations. If you wait until the background temperature drops by a factor of 10, the same energy buys 10 times as much computation. Drop the temperature by 100, and you gain 100 times as much. The relationship is direct and unforgiving, and over cosmic time the difference becomes enormous. Not a marginal improvement, but something closer to an explosion in efficiency. Thinking in the distant future becomes vastly cheaper than thinking today. Not because technology improves, but because the universe itself becomes a better computer. I find this idea quietly disturbing, because it reframes the present moment as thermodynamically extravagant. Every calculation performed now is being done in a relatively warm universe. And from a purely physical perspective, that is inefficient. It is like running a massive simulation on a computer that you know will become 1 trillion times faster if you simply wait, except the waiting time is measured in cosmic ages. A sufficiently advanced civilization, one that thinks on those scales, might look at this and conclude that activity today is wasteful, that the rational strategy is to store energy, preserve information, and delay the bulk of its thinking until the universe becomes colder and more favorable. Once that possibility enters the picture, the silence we talked about earlier begins to look less mysterious and more like the natural consequence of a calculation. Because a civilization that has decided to wait would deliberately minimize computation, reduce emissions, and slip into a low power state designed to last until the background temperature falls far enough to make waking worthwhile. leaving behind a universe that appears quiet, not because intelligence is absent, but because intelligence has decided that the present moment is simply too warm to think seriously. Once you accept that waiting might be rational, the next step is almost unavoidable, because a civilization that chooses to wait cannot behave the way we have been expecting it to behave. We tend to imagine advanced intelligence as louder, brighter, and more energetic than we are, building vast structures, transmitting across space, leaving obvious fingerprints in the sky. But that picture quietly assumes that progress always looks like activity. The thermodynamic argument suggests something stranger. The most advanced civilizations may be the quietest ones, not because they are hiding, but because silence is efficient. If thinking is expensive in a warm universe and vastly cheaper in a colder one, then the optimal strategy is not expansion in broadcast. It is conservation, which means shutting down most computation, minimizing energy use, and entering a state that from the outside looks indistinguishable from absence. Try to imagine what that would actually look like. A civilization spreads across its stellar neighborhood, gathers energy sources, builds infrastructure capable of storing power and maintaining itself across immense spans of time, and then gradually reduces its activity until only the minimum systems remain active, just enough to monitor stability, protect resources, and wait. The computers stop running large simulations. The transmitters fall silent. The industrial scale engineering halts. Waste heat drops to nearly nothing. From a distance, there is no glow, no structured signal, no detectable signature that distinguishes the system from an ordinary star system evolving naturally. The civilization has not disappeared. It has simply transitioned into dormancy, like a machine placed in sleep mode, fully intact, but deliberately inactive. This changes how we should think about megastructures, because for decades the standard picture of an advanced civilization involved something like a Dyson sphere, a swarm of collectors surrounding a star, capturing its energy output to power, enormous computational activity. Such structures would radiate waste heat in the infrared, and astronomers have searched for exactly those signatures, scanning galaxies for stars that glow strangely, dimmer in visible light but brighter in infrared, as if wrapped in artificial machinery. The expectation was that a sufficiently advanced civilization would be energetically extravagant, running massive computation continuously. But if the waiting strategy is correct, then the most mature version of such a structure would not be operating at full power. It would be idling, preserving energy rather than consuming it, radiating only the faintest maintenance level heat, easily lost in the background noise of natural astrophysical processes. The very systems we hoped would betray intelligence would instead be designed to avoid exactly that kind of detectable output. There is something counterintuitive about this, because we instinctively equate technological sophistication with visible transformation. When humans build something large, it changes the landscape dramatically. Cities glow at night. Industry leaves traces. Communication floods the air with signals. But that is the behavior of a young civilization still expanding its capabilities. An older one, concerned with long-term optimization, might do the opposite, minimizing its footprint, turning off unnecessary systems, preserving energy for a distant future when each unit of power buys vastly more computation. The galaxy in that scenario would not look engineered in the loud, dramatic sense we expect. It would look ordinary, stable, and quiet, not because nothing happened, but because the activity occurred long ago and the present state is one of deliberate stillness. When I think about this, I am reminded of walking through a laboratory late at night long after everyone has left, where the equipment is still there, carefully arranged. Power lights dim, systems idling quietly. Nothing moving, yet the room clearly built for intense activity that simply is not happening at that moment. If you walked in without context, you might assume nothing important ever occurred there. But the silence would be misleading, because the capability remains, waiting for someone to return and switch everything back on. The quiet galaxy might be something like that. A vast infrastructure paused between phases, not empty, not abandoned, but resting in a low energy state that hides its purpose, leaving us surrounded by stars that look natural, while the most consequential engineering ever attempted sits quietly in the background, conserving its resources for a time when the universe itself becomes worth waking up into. There is another idea that changes the tone of the whole picture, and it does not begin with patience or thermodynamics, but with timing. Imagine intelligence appearing somewhere in the galaxy, millions or even billions of years before us, not dramatically earlier in cosmic terms, just early enough to begin expanding while the rest of the galaxy remained untouched. Once a civilization acquires the ability to move between stars, even slowly, the expansion does not remain slow for long, because every new system reached becomes another launch point. And the process compounds. One probe becomes 10. 10 become 100. And the frontier moves outward in a growing sphere. Not linearly, but exponentially, each generation of expansion building the infrastructure for the next. Given enough time, even modest speeds allow a civilization to spread across an entire galaxy. And the time required, perhaps a few million years, is tiny compared to the age of the Milky Way. This leads to a strangely simple conclusion. The first civilization to begin this process does not merely explore the galaxy, it reorganizes it. Not necessarily through conflict, not through deliberate elimination of others, but by using resources as it expands. Stars become energy sources. Asteroid belts become raw materials. Planetary systems become nodes in a network. And the regions most suitable for long-term development are precisely the regions that an expanding civilization would prioritize. By the time a second civilization arises, the environment is no longer untouched. The most stable stars, the richest systems, the strategic locations may already be incorporated into a structure that has been growing for millions of years. The second civilization is not competing on equal footing. It is emerging inside a landscape that has already been shaped. What makes this uncomfortable is that no hostility is required. Think of a construction crew clearing land to build a parking lot. They do not search for insects before grading the ground. They simply reshape the environment according to their plans. And anything small enough to be irrelevant to those plans disappears without ever being considered. A civilization expanding through a galaxy could operate the same way, not aware of potential competitors, not trying to eliminate them, but simply using the available resources, and in doing so, closing the window for others to arise independently. The first one does not win by fighting. It wins by arriving early enough that everyone else becomes impossible. Now combine that with the waiting strategy, and the story takes on a new shape. The first civilization expands aggressively, not out of impatience, but because early expansion secures energy and matter before cosmic evolution changes the landscape. It gathers resources across vast distances, consolidates them, builds storage infrastructure, and eventually reaches a point where further expansion is no longer beneficial. At that stage, the thermodynamic argument returns, and the rational move is no longer growth but conservation. The civilization transitions from expansion to consolidation, from activity to preservation, gradually powering down the systems that are no longer necessary, leaving behind a galaxy already reorganized around its needs. From our perspective, billions of years later, we would not see the expansion phase because its signatures would have cooled and dispersed. We would not see the consolidation phase because it would already be complete. What remains is the quiet phase, the long dormancy after the work is finished, when the infrastructure exists but runs at minimal power, waiting for the universe to become colder. The galaxy would appear untouched, not because nothing happened, but because the activity occurred so far in the past that its traces have faded, leaving only a carefully managed stillness. This combined scenario resolves the silence in a peculiar way. The universe is not empty, and civilizations are not necessarily rare, but the first one to reach interstellar capability may have shaped everything long before we arrive. Then chosen to become quiet for reasons rooted in physics, we look outward expecting to find expansion, noise, and competition. Yet what we may actually be seeing is the aftermath of a process that already ended, a galaxy that has been claimed, organized, and then deliberately left in a low-energy holding pattern. It is like walking into a vast city before dawn. Every building already constructed, every street laid out, yet no one visible, no traffic, no voices. Only the faint sense that the silence is not the absence of inhabitants, but the result of a decision made long ago to wait for a better time to turn the lights back on. Up to this point, the picture feels almost too clean, as if physics itself were gently guiding intelligence toward patience. But whenever an idea fits together that neatly, it is worth slowing down and asking where it might break. The central claim behind the waiting strategy depends on a specific assumption that the cost of computation is tied to the temperature of the surrounding universe, and that the cosmic background radiation acts as the ultimate heat sink into which all waste energy must eventually flow. If that assumption holds, then cooling dramatically improves computational efficiency, and waiting becomes overwhelmingly rational. But some physicists have pointed out that this may be too restrictive, because a sufficiently advanced civilization might engineer local environments that dispose of heat more efficiently than simply radiating into the cosmic background. If you can build colder reservoirs, exploit temperature gradients, or structure computation in ways that avoid large-scale heat release, then the advantage of waiting shrinks, perhaps not disappearing, but becoming less decisive. The difference between an improvement of a factor of 10 and a factor of 10 to the 30th is not merely quantitative. It changes behavior, because the former encourages patience, while the latter practically demands it. I find this objection important, not because it destroys the idea, but because it forces the scenario to stand on physics rather than elegance. It reminds us that we are extrapolating far beyond tested engineering, imagining systems that operate across stellar distances and trillions of years. And at that scale, assumptions matter. The universe may reward waiting, but perhaps not enough to make universal dormancy inevitable. Even so, something curious happens when you step away from thermodynamics and look at cosmology instead, because a completely different line of reasoning leads toward a similar early phase of intense activity. The universe is not just expanding, it is accelerating, driven by dark energy that pushes galaxies apart faster and faster. Over immense spans of time, distant galaxies cross a horizon beyond which they can never again be reached, not because they vanish, but because space between them and any observer expands faster than light can travel, the accessible universe shrinks, not physically, but causally, leaving gravitationally bound regions isolated in an increasingly empty expanse. Now imagine a civilization capable of thinking on these time scales. If you know that stars beyond your local region will eventually become unreachable, then waiting indefinitely is no longer neutral. Every delay means losing potential energy sources forever. The rational response becomes almost the opposite of dormancy. At least initially, expand early. Gather resources while they remain accessible. Secure, long-lived stars. Redirect energy flows and consolidate matter into a gravitationally bound system that will remain intact after cosmic acceleration isolates it. In this view, the early universe becomes a harvesting phase, not because civilizations are impatient, but because the window for collecting resources is finite. Once that window closes, once the surrounding galaxies slip beyond reach, the logic of conservation returns and the civilization transitions from expansion to preservation, storing the energy it collected for the cold future when computation becomes most efficient. What is striking is that these two arguments, one from thermodynamics and one from cosmic expansion, do not contradict each other. They form a sequence. First, harvest aggressively while the universe still offers access to distant resources. Then, once enough energy is secured and further expansion becomes inefficient, reduce activity and wait. The result is a civilization that would have been extremely active long ago, building infrastructure across large regions of space, and then gradually becoming quiet as the harvesting phase ended. By the time a young civilization like ours appears, the energetic period would already be history. Its heat signatures dispersed, its engineering cooled, leaving only a silent, consolidated system optimized for long-term storage. This layered logic makes the silence harder to interpret because it no longer points simply to absence or even patience, but to a timeline that may have unfolded long before our sun formed. The most visible phase would have occurred billions of years ago, followed by a long interval of inactivity designed to preserve resources, and what we observe today is only the quiet remainder of that process. From here, the sky begins to look less like a place waiting to be filled and more like a landscape already shaped. Its most energetic events buried in deep time, leaving us in a universe that appears untouched, while the consequences of earlier decisions remain quietly embedded in its structure. There is something subtle about the way we search for intelligence in the universe, and it hides in an assumption so natural that we rarely notice it. We look for signals, radiotransmission, laser pulses, unusual infrared heat, structured emissions that stand out against the randomness of stars. The entire philosophy behind SETI is built on the idea that intelligence announces itself by doing something energetic, something detectable, something that disturbs the quiet background of nature. That assumption comes directly from our own behavior, because we are noisy. Our planet leaks radio waves in every direction. Radar sweeps spill into space. Satellites chatter continuously. And even our most ordinary technologies broadcast signatures that would look artificial from light years away. If another civilization were nearby and listening, they would not need to try very hard to notice us. The glow, not visibly, but electromagnetically, and we assume others would do the same. But that assumption quietly depends on youth. We are a civilization in its early energetic phase, expanding communication networks, increasing power consumption, and running computation continuously without worrying too much about thermodynamic efficiency. The waiting strategy we discussed earlier suggests that this phase may be temporary, Something civilizations pass through before realizing that broadcasting wastes energy and large-scale computation is more valuable in a colder future. Once that realization takes hold, the incentives flip. Instead of maximizing output, a mature civilization minimizes it, reducing emissions, shutting down unnecessary systems, and entering a state where activity becomes rare and carefully controlled from the outside. Such a civilization would not glow with artificial noise. It would fade into the background, indistinguishable from natural astrophysical processes. This creates a detection problem that is almost philosophical in nature. SETI is designed to find activity, not existence. It listens for civilizations that are transmitting, building, or consuming energy at large scales. But if the most advanced civilizations are deliberately quiet, then the very behavior that signals maturity also makes them invisible to our methods. We are searching for the loud phase, the brief window when intelligence is extravagant and inefficient, while the long-lived phase may be defined by restraint. It is like trying to estimate the population of a city by measuring how much noise it produces. At noon, the method works reasonably well. Traffic roars, construction echoes, crowds move, and you infer a bustling population. But at 4 in the morning, the same city becomes silent, and the noise meter suggests emptiness, even though millions of people are still there. Asleep, waiting for morning. The instrument has not failed. It is simply tuned to activity rather than presence. Astronomical searches for megastructures face a similar limitation. We look for Dyson spheres by searching for waste heat, assuming that enormous computation must radiate energy in the infrared. Yet a civilization committed to long-term efficiency would reduce computation to the minimum necessary for maintenance, producing almost no excess heat. A dormant structure could surround a star and still appear nearly natural. Its emissions so faint that they blend into ordinary stellar behavior. The absence of strong infrared signatures does not rule out intelligence. It only rules out intelligence that is actively spending energy. The quietest systems, the ones preserving their resources for trillions of years, would sit below our detection threshold by design. This shifts the interpretation of silence in an uncomfortable direction. We have often treated the lack of signals as evidence that civilizations are rare or non-existent, but it may instead reflect a mismatch between what we expect intelligence to do and what it actually chooses to do once it becomes sufficiently advanced. We are listening for conversation in a room where everyone has agreed to stop speaking. Not out of secrecy, but out of efficiency. The sky appears empty because our methods depend on noise, and the behavior we are trying to detect may systematically eliminate noise. When you think about it that way, the quiet galaxy stops looking like a failed search and starts looking like a methodological blind spot. A universe that may contain intelligence arranged in ways that leave almost no direct trace, forcing us to confront the possibility that detection requires a completely different approach, one that does not rely on signals, but on subtle influences, faint irregularities, or patterns that suggest long-term organization rather than immediate activity. And until we learn how to look for those, the silence we measure may say less about what is out there and more about the kind of intelligence we have been expecting to find. There is a temptation, after building this entire picture, to imagine that patience solves everything, that a civilization intelligent enough to harvest resources, go quiet, and wait for the universe to cool, has effectively escaped the dangers that limit younger species. But physics has a way of quietly reintroducing uncertainty at the deepest level. And one of the most unsettling possibilities does not involve war. entropy, or resource exhaustion. But the stability of the vacuum itself, the universe we inhabit, is defined by fields, not empty space. And one of those fields, the Higgs field, determines the masses of fundamental particles, and therefore the structure of atoms, chemistry, and everything built from them. Measurements suggest that this field may not sit in the lowest possible energy state, but in a metastable one, like a ball resting in a shallow valley separated from a deeper valley by an energy barrier. Quantum mechanics allows tunneling through such barriers, meaning that somewhere, at some time, the field could spontaneously transition to a lower energy configuration. If that happens, a bubble of true vacuum would form, and the boundary between the two states would expand at the speed of light, rewriting the laws of physics as it passes. There would be no warning, no signal traveling ahead of it, because any signal moves no faster than the boundary itself. One moment, the universe follows familiar rules. The next moment, those rules change, and structures that depended on the old constants would no longer hold together. What makes this disturbing in the context of waiting civilizations is that patience offers no protection. A civilization could store energy for trillions of years, build stable infrastructure, minimize computation, and prepare for the cold future. Yet vacuum decay ignores all such preparation. It is not a problem to be engineered around, but a statistical feature of the underlying physics. The probability per unit time may be unimaginably small, yet over cosmic durations it cannot be dismissed entirely. The longest-lived strategies become the most exposed because they depend on the continued stability of the laws themselves. In that sense, the universe offers no absolute guarantee, only a window of reliability that has lasted so far and may continue indefinitely. But never with certainty, even without such catastrophic possibilities. There is another, quieter limit imposed by information theory. The amount of computation any civilization can perform is finite, constrained by the total energy and the physical size of the region it controls. The Bekenstein bound tells us that information storage scales with surface area rather than volume, implying that even the most advanced systems cannot compute infinitely. Waiting for the universe to cool does not unlock unlimited intelligence. It merely allows more efficient use of a fixed budget. The strategy is optimization, not transcendence. Intelligence in this picture is not escaping physics, but negotiating with it, choosing when and how to spend finite resources to maximize thought before the universe's usable structure fades. Taken together, these limits reshape the meaning of the silence we started with. The quiet sky no longer suggests emptiness, nor simply dormancy, but a universe where intelligence, if it exists, is engaged in a careful balance between opportunity and constraint, harvesting early while resources remain accessible, conserving energy as temperatures fall, and accepting that even the most patient plan operates within boundaries set by the underlying laws. We, by contrast, occupy the earliest energetic phase, still spending freely, still broadcasting, still interpreting silence as absence, because we have not yet learned to see stillness as a deliberate state. The possibility that the galaxy is quiet because it has already matured, because activity gave way to preservation long before our planet formed, reframes our place in a subtle way. We are not late to an empty stage, nor surrounded by rivals, but perhaps living during an intermission, a long pause between phases of cosmic activity, when intelligence, having gathered what it needs, chooses not to act until the universe itself becomes more favorable, leaving us looking outward at a sky that appears still, while the deeper story may simply be waiting for conditions that have not yet arrived,